Ready to go in? Hopefully the microphone is working, so let's jump back in. I wanted to look at some case studies for additive manufacturing now. So we're sort of moving away from hybrid and repair into some case studies. And so this is an example of directed energy deposition. The plate you see on the far right is what this case study is about. It's a sprayer plate that's again made by laser-based DED, stainless steel. And they designed it, built and installed the plate in less than 5 days. And it was the first A part printed on the USS Macon as part of the Navy's afloat additive manufacturing program. So they actually put a machine on the boat and used it to create parts. And again, it was a nice application. I talked earlier about laser shock peening, and I guess technically laser shock peening could be considered to be a hybrid technology because it is two separate processes that are being stuck together. And so I think we've talked about this pretty well, so we don't need to belabor it. But effectively, remember, it involves using a laser, a high pulse laser, to create a deformation wave. And this can be used for primarily for lowering surface residual stresses, but also, as we'll see here in a minute, can be used for finishing as well. So again, it's sort of a fatigue life and a part performance issue. This shows an example of how that works. There's a 3/16 stainless part that they show with the laser shock peening, and basically the upshot of all of this is that even depending on the angle that's presented to the laser, because the laser basically is always traveling in Z, but the surface that it hits can vary in terms of the angle. And so this shows basically, depending on the rotation of the surface being shock peened to the laser itself, that we get if we look at this blue dot, the blue triangles, we see that it's very low and that we're able to get, to reduce the surface roughness of the part really at all angles. And over here, sort of the upshot of this is that in some cases we're able to reduce the surface finish, to improve the surface finish by doing the laser shock peening. So again, I guess to move towards a summary of where we're at, then what we have is we have the hybrid processes. It's typically additive manufacturing plus machining, because that's where the real value comes in. But it can be other things. You know, the shock peening would be an example of that. The best value of hybrid is when it's necessary to do the subtractive processing during the build. That tends to justify the use of a hybrid type machine. And then, of course, the DED, as we well know, is well suited for part repair. So we can use it, you know, in that capacity in a wide variety of materials and a wide variety of part applications to do repair. So I think it's a very important part of the additive manufacturing technology base that we have. So having said that, I was asked to say a little bit about myself. So we're going to switch here. We're going to switch gears for a little bit. I don't think we're going to have 30 minutes worth of me talking about myself, but so we do have a little bit. I do have a little bit of material to show here. So I started my career at Texas in 1979. Those of you who have maybe graduate students, what you have to appreciate is in 1979 it was possible to be a graduate student one day and then to be a professor the next day. What we do, certainly in Texas, is it's really required to go off and do a postdoc, or in some cases maybe multiple postdocs or experiences. But that wasn't the case in 1979. So I finished at Stanford in June, and in August I started in Texas as a new assistant professor. So, and I'd like to think that they got their money's worth out of me, but anyway, I spent, basically the point of this is to say that I spent my entire career in the mechanical engineering department at the University of Texas. So I didn't jump jobs. I was very happy to be where I was. I'd made a deal with my wife. We had been married when I graduated with my PhD. We'd been married for 4 years, and we were in California. I promised her that if we could go to California, I could do my graduate studies. I promised I would come back to Texas and stay there. So I made good on my on the agreement, on the contract. So here's some photos of me back when I first started in Texas. This was right before I graduated from Stanford, right before my PhD. This was actually, it's 1987. It was about the time I got into additive manufacturing. So that's where I was. And so this is the sort of the story of additive manufacturing at the University of Texas. It was in this 1986 to 1988 time frame that a student, who was a master's student at Texas, Carl Decker, he invented laser sintering. The original patent on laser sintering technology was just him. He was the sole author on the patent, so there were no other professors or anything on that. And I mentioned that at least based on the royalty stream for laser sintering, I was consider myself a 10% inventor. I really didn't do anything with the hardware, but I did a lot of the early materials for laser sintering. And so in fact, actually it was in '87 that Carl came to my office and said, he was having materials issues with a manufacturing process. And so I said, okay, fine, I'll help out. I'm glad I did. I sort of had this sort of nightmarish vision of what would happen if I'd done like many of my colleagues do, and just sort of said, no, I'm too busy, go away. Who knows what would have happened then. But anyway, it was in 1988 that Joe Beeman, another faculty member at Texas, who was Carl's master's supervisor, formed this laboratory for freeform fabrication. It was formed in 1988. I took over as the director of the center in 2007 and ran it till 2020, so for about 13 years. And then in 2020, it converted to the Center for Additive Manufacturing, Design, and Innovation. I think we've talked about that already. So anyway, I guess for me, when I think of the main achievements, so one, of course, was producing this first metal part. It was a copper. Basically, we dealt with copper tin and lead tin solders to produce this part. It was about 10 centimeters across, and we did this in 1990 was when we published the work, and it was, but really by a long shot, the first direct metal part made by modern additive manufacturing. Well, we talked about balling. I think I could skip over this one. We've already been down this road. That balling we also saw first observed in May in our lab. I show here the first page of the first materials patent for modern additive manufacturing. You can see the names. I was the lead author. Harris Marcus, Joel Barlow, and Joe Beeman are all professors. And then Carl Decker, of course, was the inventor of the process. And what we did is we had developed the rationale for using multiple material systems in selective laser sintering. It's sort of you read the patent. It was basically something to kind of melt and glue the parts together, the powder together, and then the feedstock itself. So we use this for a variety of applications. The metal work that we did was based on this. I'll show you some ceramic work that we did that was also based on this concept. So this is the first article on additive manufacturing published in the Materials Journal, TMS. It was published in JOM in 1990, and it's a little bit of a high type article. You see the title, From Computer to Component in 15 Minutes. Well, we're not quite there yet, but anyway, it's the integrated manufacturing of three-dimensional objects. So, and again, this was, I was the last author on this paper, but again, it was this group of 4 faculty. 3 of us were materials people. Joe was kind of the machine builder, as it were. They put this article together. And so we've talked about the SFF Symposium. Again, several from this university have attended in the past. It's a meeting that's held in Austin every year. And to speak about the conference itself, it's the oldest continuously running annual topical research conference on additive in the world. And these days, there probably are maybe 40 conferences like this that have varying degrees of academic intensity that one could go to around the world. But we're the oldest one. It predates the oldest additive manufacturing journal by 5 years. So if you really want to know what the what was going on, like right back at the very beginning, right at the Big Bang, this is probably the best source. There is no other source. Again, if you remember that additive manufacturing, depending on where you put the stake in the ground, additive, typically, I say it started around 1987 when Chuck Hull commercialized the first SLA machine. So we're talking, this conference started in 1990, just 3 years after that. And so it captures a lot of the really early work. There's 4,300 presentations made. That's I don't think that includes 2024, so that's up a little bit. 3,100 papers published in the proceedings, which comprises 27,000 pages of additive manufacturing research findings. And I would, there were, 2023 meeting, there were 589 attendees. I think that 2024 we had about the same number. And I would also rush on to say that the proceedings articles are available for free download on the site, all 30 years of it. And I think maybe I can, let's see if I can make this work. Let's just to show you, this is the web page for the conference. The next meeting is August 10th through the 12th. Everyone's welcome to attend. Come to Austin. It's very hot, but we have a nice meeting. Let's see, I was looking for the archive here. The proceedings, let's see, if you just come up here to proceedings archive, it jumps down here. And so what we have is all from 1990 to 2024, we have all the proceedings. It's not particularly searchable, but basically what our thinking is that you're off doing your research, you find an article that looks interesting, so you have the citation, but you want to look at the article. So basically, if you have the citation, you know the year number. So what we could do is we could pop in to that year, and then like 2001, and then you see here's the list of the table of contents. So we can grab a Sumontas article here. I just click on it, and it pops open the article. So here it is. Instead of this, the full article, you can do a save as and download it. It's just free access. So it's the entire SFF conference proceedings. So if you find any article in additive that's SFF, you know that you can go to the website and download it at no cost. Okay, so anyway, I was a member of the organizing committee in 1990. Harris Marcus, who's sadly now deceased, was the first chair. He was the chair from 1990 till 1994 when he retired from the university and left, and that was when I took over, and I did it until I retired in 2022. So, anyways, that's the conference. In the conference proceedings, the very first article in the proceedings was one that I wrote again with my faculty colleagues that were really involved with laser centering back in the late 1980s. And again, it's simply we call the technology solid freeform fabrication. Now it's 3D printing or additive manufacturing. It's the same thing, but and the conference, it turns out, we called the conference the SFF Symposium, and I can tell you in 2009 we had quite a quandary because ASTM had established the quote official standard name for the technology as additive manufacturing. And so I wasn't sure. It's like, well, what do we do? By 2009, we'd been running this meeting for almost 20 years, and we had a pretty good brand name for the meeting. And so we really didn't want to change the name, but we also wanted to, we wanted to be modern and up to date and accurate. So I actually had a long conversation with our scientific committee. We have a scientific committee separate from the organizing committee, and I asked their advice, and what we came up with was to sort of shorten the name to the SFF Symposium, which is what everybody called it, and we're not going to really associate solid freeform fabrication with it. But then we add on as a sort of a afterthought that it's an additive manufacturing conference. So the official name now is like the annual International SFF Symposium, an additive manufacturing conference. So it's kind of a long name, which sort of captures all of the different pieces. Okay, the first part that we made in 1990 was this copper. Well, it really wasn't a commercial metal, but in 1996 or so, 1999, and I guess we've already been over this part too earlier. Suman Das, who's the first author on this paper, did the work. He actually designed and built this high temperature workstation that had a powerful laser. It was able to heat up to 800 or 900 degrees centigrade, the work chamber, and we were able to produce some really nice parts here. So this is fully dense titanium 6.4. This was done again 1999, which is about 3 or 4 years before the first quote commercial metal machine really hit the market, which was a European machine. I spent a lot of time talking about F-42, the standards committee. I was involved by, it turns out that in the fall of 2008, there was a 15-person team that was met. It was put together by Brent Stucker, who is, where is he now? I can't remember where he is now, but I won't rehearse his whole career. He wound up at ANSYS because he was doing, he had developed a company, 3D Sim, to do modeling of additive manufacturing. It was kind of a nice program. It basically, you sort of input the machine parameters and it output only for titanium, Ti-64, it output what the microstructure and properties would be. So it was kind of a nice program. ANSYS bought him out. He moved to ANSYS, then he wound up at working for ASTM. He may be at 3D Systems now. But at any rate, he was at this time he was involved with the society, the American Society of Manufacturing Engineers, and they had a rapid prototyping committee that he was involved with, and they basically said, look, it's SME is a fairly applied organization, right? It's not a bunch of scientists, it's a bunch of users. And so they said, look, we have a demand for standards in additive manufacturing. So Brent was charged to sort of search around and see what was out there. And he came back and reported and said, really, ASTM is really where we need to be. in terms of what we want. And so he went to ASTM. I showed the headquarters here. It's just north of Philadelphia in Pennsylvania in the U.S. And he basically said, how do we make standards with using ASTM? So the director of the facility, a guy named Pat Picarillo, said, well, what we need to do is we need to have sort of a constitutional convention here. We need to plan a constitutional convention. So we need to get some people together in the field and talk about how can we organize a meeting of a bunch of people and have an agenda that will allow us to move forward with organizing a technical committee within ASTM. Once that's done, then we'll be empowered to start writing standards. So anyway, so I was part of that in the fall of 2008, and we assembled the Constitutional Convention in January, I think it was around the 10th or 11th, in 2009, also at ASTM headquarters. And we, after a couple of days of meetings, it was again about a little over 100 people there, we actually voted to form ASTM Committee F42. And so that's when the term additive manufacturing actually became the quote, official standard term for the technology. Again, we talked a little bit about that earlier this week. Anyway, also, I've also mentioned since 2014, I've been on the terminology committee, which again is sort of in charge of the dictionary of additive manufacturing. So if you don't like a definition of something, it's my fault, I guess. But I think we've done pretty well overall. Did I tell you the story about I think I told you about plasmoidy. Said for those of you that grapple with language, I should probably mention this. Plasmoidy is worked at Syntec for many years. He was and still is the chair of this committee for doing terminology. These joint committees have to have a home either at ASTM or ISO, and this committee's home is in ISO. And so Klaus convenes this group. We were doing Zoom meetings, years before COVID, to make this work, because we had representatives from Asia, from the United States, from Europe, all there. We're all part of this because we had to make sure we covered the world. And so the problem with the committee is that we're a bunch of engineers, and our language skills are, I don't know how it works in India, but in the U.S., typically if you're strong in mathematics, your language skills are not very good. And so we would often, as we were writing definitions, have problems with how the language, what the language and what the grammar should be. So yeah, again, by the way, this standard has, I don't know, I think it's like 130 or so definitions now. They're all related to additive. So anyway, so the way the story goes is we were in one of these Zoom meetings, and we had this quandary over how to make the language work. And so Klaus, who is from Sweden, said he sort of stopped the group and said, "Why don't we table this to the next meeting? And in the meantime, I will ask my mother." And then he went on to explain that his mother in Sweden was actually taught English. She taught language in their school system, and she was an English teacher. She taught English, so actually her grammar skills were very good, perhaps better than a normal English speaker. And so he did that, and she gave the answer. So we had the answer back in the next meeting, so we could continue to do our work. But then from that point on, even to today, whenever there's any language problem, someone will always say, "Plus, go ask your mother." And so we have her as almost a unofficial member of the committee to help guide us with the language. There was I didn't really mention, I don't think I really mentioned this directly, but there's a paper that I put together that I consider to be really a masterwork of materials for additive manufacturing. It's this, it was published in the SERP Annals. They do these massive review articles, and this one is on materials for additive manufacturing. You can see it's 23 journal pages long, 346 references, and it's at least as of a year or two ago, had received over 1,300 citations. The author list is really, for the most part, kind of a who's who of additive manufacturing. I was the lead author. Jean-Pierre Cruz at KU Leuven is very well known, now retired. I consider his claim to fame is that he was one of the founders of Materialize, which many of you may know. Materialize is a company that really did a fantastic thing back in the early days, back in the, I think it must have been in the 90s. The problem, what it did is they developed their magic software, which really was, it was like a cure for COVID. I mean, it was absolutely unbelievable technology, because what it could do is you could basically create an STL file, and it turns out in the old days, maybe even today, it turns out that for the program to work, every single node in the tessellated surface has to be continuous and can't overlap with itself. So we're talking millions of point data that one in the wrong place can kill the build. And what Stratasys did is was able to sweep through these solid models and locate and repair those errors. Before that, we were just sort of hoping and praying that the STL file would run. But after Magix, we don't even think of it anymore. You just run it through Magix and off you go. Well, anyway, that's Jean-Pierre Cruz. Ming Liu is a professor at Missouri University of Science and Technology. I consider his claim to fame is he did this sort of ice additive manufacturing, where you could build ice articles. So what he did is instead of heating the chamber for the build, it's sort of an extrusion machine, but he would extrude water, and the chamber was frozen, so the water would come out of the nozzle and then would instantly freeze. And so you could build these ice works, as it were. And you might think, okay, well, what you do, you make ice sculptures, right? And they do. But it turns out they could also create, the main purpose of doing this was to create patterns for casting. So what you can do is you can create an ice pattern, and then fairly quickly create the mold cavity, and then just melt the ice out, and you're done. So that's me. Gideon Levy is now also long retired now. He was the most popular feedstock in additive manufacturing today is nylon. And his group when he was at the company, I'm trying to think what the name of it is. It's in Switzerland. But anyway, he was working for St. Gallen's, University of St. Gallen's, I guess. But they had an industrial side entity, which I can't remember the name of. But it was his group that actually developed nylon for additive manufacturing. And then David Rosen, maybe some of you know David Rosen, Georgia Tech professor, did a lot of work with stereolithography, retired now and is working for A-Star in Singapore. But then I also added Allison and Adam Clear. Allison Beasy, both of these are young junior assistant professors, at least they were at the time. Allison is at Penn State University and is really a very well-known metal expert. Adam Clear was, when we did this work, when we wrote the paper, he was at the University of Nottingham in the UK. They have a humongous, large additive group there. But he's now moved to Canada, is on the faculty, I think maybe University of Waterloo, where he's moved to. But anyway, it's quite a prestigious group of people. I've actually talked with Adam. He's not coming to the SFF this year because his wife is having a child at that time, which is certainly an allowable excuse. But I guess while on the subject of children and the SFF, Allison Beasy, we give so-called FAME awards, Freeform and Additive Manufacturing Excellence awards. We give a junior award and a senior award every year at the meeting. And of the senior faculty here, of the senior investigators, all of us have won that award. Both of these junior faculty have won the junior award for faith. But Allison had a problem in August. She had just had her first child, and the child was, I think, maybe 4 months old, 5 months old, and so she wanted to come, but was concerned about her child. So I actually sort of sweet talked my daughter, who was a mother herself, late 30s at the time. I said, look, will you come babysit this kid, just a few times so she can come to the meeting? And my daughter was willing to do that. She owes me favors anyway, so she was willing to do it. So she actually came, like for the awards banquet and some of the other events. My daughter came and sort of did child care for Allison's kids. So I was very happy with that. Okay. I mentioned that the materials handbook is this encyclopedia of materials knowledge, primarily for users of the technology. And they just in 2020, so 5 years ago, they came out with the first of 2 volumes on additive manufacturing. It's volume 24 and volume 24A. 24A is sort of design and applications primarily for metals, whereas volume 24 is sort of the general overview of the technology. But I and Terry Rollers wrote the introduction for the 2020 issue. It was an absolute pleasure to do that. I've had the opportunities on many occasions to work with Terry. He's a fine gentleman and an excellent co-author. I also, with Terry, wrote this history of additive manufacturing, which is largely what I think we discussed at the first session here this week. But if you want to know all the nitty-gritty details about the history, it was me and Joe and Terry put this together, and so you can see some familiar graphics from that. And there's quite a bit that I didn't really talk about here in the interest of time. So this is within the Materials Society. It's the Mining, Metals, and Materials Society. It's centered in Pennsylvania. It's an international organization. We meet twice a year. But and again, I mentioned it was a 13,000 member society. Just this year in last March, I was successful in becoming the board of directors slate nomination for what's called the presidential cycle rotation. So if everything goes according to plan, in March of next year in San Diego, I will become vice president of the society for 1 year, and then following that, president of the society for 1 year. Following that, past president of the society for 1 year. So it's a 3-year term of service, but it is something that I'm very excited about and really looking forward to doing it. So I think it's an outstanding society. I was on the board of directors right before and during COVID. And we'll skip past these things. The other thing I think that's noteworthy is I was elected a fellow of the society in 2011. This is the fellow. Most societies, ASME, IEEE, all have fellow designations. ASM International, but TMS is a little unique in that they limit the total number of fellows at any time to only 100 people. So it sort of makes it kind of a prestigious elite group. So I'm very proud to be part of that. So here's the last slide. It's some other recognition. I was really kind of happy, and just last September, there's a conference called the Laser Assisted Net Engineering Conference. It meets I think maybe every 3rd year in Bavaria, and their career award they call the Night of Laser Technology. It's kind of a fun thing because they actually have a knighting ceremony for the recipient. And so what we see here is this is Rainer Papave, who runs the Fraunhofer, the IPT that that had put together the failed hybrid machine back in the early days. Yeah, he's actually running that Fraunhofer now. So he was the dubber. So there's a little sword here. So I was down on one day, just like in the movies, and we had that dubbing. The other fun part about it is next year. I guess I meet every other year. Next year, when the conference meets again, my job as the immediate task recipient is to do the knighting for whoever the next person is. So we'll pass it that way. So I'm excited about that too. I've received a couple of Lifetime Achievement Awards. ASTM gave me one. Singapore University of Science and Technology gave me one. And I think there was one other one in here somewhere. But anyway, so we have those. The Reinhardt Award 2022 was for contributions in the realms of terminology standardization. So it turns out that Cosmovic and I both won that award that year for our contributions in standards. Got the Sargent Award. It's a Outstanding Manufacturing Award from SME. The FABLE Award I already mentioned. And down here at the end, back in the early days, I actually had a von Humboldt Foundation Fellowship. Von Humboldt, if you're familiar with the U.S. Fulbrights, the Fulbright is designed for scholars, to pay scholars in the United States to go abroad and to study. The von Humboldt in Germany is kind of the backwards version of that. They pay foreign scientists to come to Germany to study and to do research. So I was able to get one of those. So I spent a year in Germany with my family. We were at this Biometallurgy laboratory. The Max Planck Institutes, if you're not familiar with those, if you're familiar with the German Fraunhofers, they're just like the Fraunhofers, except they're more science-based and not so applied. If you're not familiar with the Fraunhofers, it turns out Germany has about 30 or 35 of these Max Planck Institutes, each of which has a thing. This one was powdered materials. And so I was actually there working. It was like a research lab type situation, type setting in Stuttgart, down in the Black Forest in southwestern Germany. So, and then the first SAR award I got was in 1986. Again, it was a year before I started the big additive, so it's a really long time ago. ASM has this outstanding teaching award for young faculty, and I actually won. It's called the Bradley Stock Award for young teachers of metallurgy. Certainly, I was young back then, but not anymore. So, okay. So anyway, so that's basically me. We've got about 5 minutes left, and I think I'm at the end of my. Yes, I'm at the end of my show here. So I guess we're in a position where we can take a little bit of time and have some questions before we take a 15-minute break and have tea. So if there's anything about hybrid or repair you'd like to talk about.
Any queries from the participants? Can we take in the tea break?
Yeah.
Are we working on metal composites as of now?
Where are we working on metal
Composites.
composites? Oh, have I or where is there work? Yeah, I have not worked on metal composites. Certainly, there is a small slice of materials that is composites, and I can tell you that the composite work in additive is typically chalk fiber or particulate composites. Largely, there's I think one machine that somehow can manage to do continuous fiber in additive. I'm not sure how it works, but obviously, it's a matter of these are powder-based processes. It's a matter of mixing the powder together. I think I've seen some aluminum silicon carbide. That's a standard metal matrix composite. I think I've seen some aluminum silicon carbide work, but again, it's it's not widespread, but it is out there. You should be able to find it. Right. Yeah, it's a good question.
Yeah, we can have a tea break and then.
Okay, sounds great. Yeah, let's go have some tea.
Yeah, thank you.
Great, I'll see you. 11:45, we'll meet back for the future, where everything's headed.